All right, today we're going to look at section 7.8, improper integrals. What is an improper integral? Well, if you want to look at the beginning of the section, you'll see a rundown of what they're calling improper. One is if it's going to infinity from a to infinity. Another one could be from negative infinity to b, or it actually can be open-ended on both sides from negative infinity to infinity. What we are going to do very strictly is rewrite them as limits so we can actually evaluate it, because we can't evaluate an integral at infinity, but we can evaluate limits at infinity. Now, I know you guys can get kind of sloppy in this, so let's see what I'm talking about. Let's look at example 1 out of the book. We have the integral from 1 to infinity of dx over x. Now you're tempted to jump straight in and call that, well, you know that's a natural log, and then evaluate it from infinity, 1 to infinity. But I'm going to hold you to this, being very strict about how to redefine this. So I'm going to let the limit as b approaches infinity, I'm going to call this from 1 to b of dx over x. In other words, I just redefined that top one instead of infinity. I define it as b, and we're talking about what happens as b approaches infinity. Because the fundamental theorem of calculus says I can evaluate it at constants, but it says nothing about evaluating it at infinity. Well, now that I have this, I know the integral from 1 to b dx over x is simply the natural log of x evaluated from 1 to b. Don't forget to be strict about your limits, so you're going to carry them down with you every time the limit as b approaches infinity. So what is this? Well, let's go ahead and use the fundamental theorem of calculus to say that that's the natural log of b minus the natural log of 1. And you know the natural log of 1 is 0. So basically, now we're evaluating the limit as b approaches infinity of natural log of b. Well, this one, as you learned at the beginning of last year during limits, is one that you can evaluate by straight substitution. By substituting infinity here at natural log of infinity, you know by the natural log graph it's going off to positive infinity. So that is in a case of one that is indeed divergent. It's going off to infinity. Let's look at example 2. You now have the integral from 0 to infinity of e to the negative x dx. Once again, yes, I know you can jump in and start evaluating this, but I want you to very strictly say the limit as b approaches infinity from 0 to b of e to the negative x dx. Well, I almost have an e to the u here. I just need a derivative. So if I bring a negative inside and bring a negative out, now I have an e to the u du. So I can evaluate this. So the integral here is the negative e to the negative x. And we're evaluating that from 0 to b, and don't forget to bring your limit down every time the limit as b approaches infinity. So we're looking at the limit as b approaches infinity of negative, I'm going to put this all in parentheses now, e to the evaluated b, negative b, minus e to the 0, which is the limit as b approaches infinity of negative 1 over e to the b minus 1. Well, now we can go ahead and substitute infinity in there, and I get negative 1 over e to the infinity minus 1. And this is heading off to infinity, and 1 divided by infinity, 1 divided by a very large number, you know, to be 0. So it says negative 0 minus 1, or negative 1, and negative 1 is positive 1, and now you've evaluated. So this one is not divergent. Let's look at another one that converges on a number. We're going to look at the integral from 0 to infinity of 1 over x squared plus 1 dx. And one thing I like about this section is it makes you guys go through your rules of integration and your techniques and see what you can do. Hopefully you recognize this one as a chapter 5 problem in inverse trigonometry, because it's in the form of u squared plus a squared. So, but before I get there, don't forget to be strict about your limits. The limit as b approaches infinity of 0 to b of 1 over x squared plus 1 dx. Now you should recognize that as an arctangent problem. So that's arctangent of x evaluated from 0 to b, and of course it's the limit as b approaches infinity and the limit as b approaches infinity of arctangent of b minus arctangent of 0. Well, you know the tangent is 0 at 0, so that goes to 0. So we're really evaluating the limit as b approaches infinity of arctangent of b, which is, what is the arctangent of infinity? Well, this is where it helps to know the graph. If you recall, arctangent does this, where it has two asymptotes. It has an asymptote at y equals pi over 2 and negative pi over 2. So as this gets very large, it's getting closer and closer to the asymptote. It's getting closer and closer to the value pi over 2, which is the value of our integral. Okay, thus far we've looked at, let's stick with these divergent ones because of infinity. So let's look at example 3. The integral as goes from 1 to infinity, as x goes from 1 to infinity, of 1 minus x e to the negative x dx. Well, just like all the rest, we have to decide which technique we're going to use, and this is actually going to be an integration by parts. So let's first of all say the limit as b approaches infinity of 1 to b of 1 minus x e to the negative x dx. And I'm going to if I'm doing this by integration by part, you may recall that our dv is always the e1, e to the negative x, and my u is going to be 1 minus x, du is now negative dx, and v is negative e to the negative x. The limit as b approaches infinity of we're ready to use integration by parts and evaluate this. So ub minus v du. So ub is 1 minus x. V was negative e to the negative x minus the integral of v is negative e to the negative x. Du is a negative dx. So what we have is the limit as b approaches infinity of negative 1 minus x e to the negative x plus, it's set up really nice because that's a du that we're looking for there. So it's e to the u du, which is simply e to the u, so the integral here is e to the negative x. Now we're evaluating this from 1 to b. Well, I might do a little bit of algebra before I try to evaluate this to make it a little bit simpler. If I factor out at e to the negative x, I'm left inside with that. I'm going to go ahead and distribute this through negative 1 plus x plus 1. And remember, evaluating this from 1 to b, and of course it's the limit as b approaches infinity. So the limit as b approaches infinity, you guys notice I'm painstakingly writing down this limit every time. I want you guys to do the same. These ones are going to cancel out. So I'm left with e to the negative x times x evaluated from 1 to b. We're almost there. Extend this page. All right, so now using the first fundamental theorem of calculus, that's e to the, I'm sorry, let's back up a little bit. Let me rewrite this. I'm not going to evaluate it yet. That's x over e to the negative x from 1 to b. Now I'm going to use the first fundamental theorem of calculus that says that can be b over e to the negative b minus 1 over e to the negative 1. I'm sorry, let's back up. That should be a positive because I moved it there, so that's positive there and that's positive there. All right, now we can evaluate this. When I put an infinity in, I got infinity over e to the infinity minus 1 over e. So guess what? We're going to come back up to L'Hopital's rule. So let me rewrite that on another page. So I'm looking at the limit as b approaches infinity of b over e to the b minus 1 over e. Now, because it's infinity over infinity, it's a L'Hopital indeterminate, and I can then, by using L'Hopital's rule, take the derivative. Now, I'm just concentrating on this part here because the limit as b approaching infinity, this is still minus e to b. So that's the same as the limit as b approaches infinity. I'm doing this in terms of b, so it's 1 over e to the b. So I'm treating b as my x when we take the derivative there, minus 1 over e. Now when I put infinity in there, you see that is going to 0 because it's 1 over infinity minus 1 over e, and we get to our answer, which is negative 1 over e. Okay, that was example 3. All right, I'm going to look at just one more example, but I do want to talk about sometimes it's improper if it's discontinuous. And you can look at, I believe this is on page 544, and there's look at example 8, and you'll see a good discussion of what happens. I'm going to work through only one more example with you. I'm going to look at example 6, and we're going to look at from 0 to 1 of dx over cube root x. The problem here is not it's going to infinity. This one's improper because it's when you're trying to divide by 0, and so 0 is not actually defined here. So I'm going to talk about the limit as let's call it a approaches 0 from the positive side of a to 1 of dx over cube root x. Well, just rewriting this, that's the x to the negative 1/3 dx. So we're talking about the limit as a approaches 0 from the positive side. Evaluating this integral, you add 1 to the power, so x to the 2/3, divide by that 3/2, evaluate it from 1 to a. So it's the limit as a approaches 0 from the positive side of 3/2 times 1 to the 2/3 minus a to the 2/3. Well, now I can put 0 in. For a, it's heading to 0. So this is really just 3/2 times that 1. And so the answer here is indeed 3/2. All right, there's some other examples in the book. If you wanted to look at them for further help, I'll be around here in a few minutes to see how you guys are doing. We will have some book work out of this stuff.